Okay guys, welcome to our section on the zeros of a polynomial. We're going to talk a little bit more about some strategies of finding zeros of a polynomial. Previously, we used synthetic division to prove if something was a zero and kind of had used that to help us factor down a polynomial so we could continue to find zeros. Now, in this section, we'll see some more tips and tricks and some ways that we can kind of streamline that process and a few more concepts about polynomials. Okay, so let's start with the fundamental theorem of algebra. And what the fundamental theorem of algebra mentions about a polynomial is that if you have a polynomial with a certain degree n, okay, which is just some positive number, then there's at least one zero in the complex number system. Remember, that means real and imaginary together, okay? And you can just remember that the total zeros is always equal to the degree. Okay, so your real and your imaginary zeros total up to be the degree. Okay, now that's not necessarily the unique zeros, so some of them may be repeats, so it doesn't show up so nicely, but overall, we know that the degree is equal to the number of zeros that you'd run into in the complex number system. All right, now moving down, we see the linear factorization theorem, which says basically we can break any polynomial down into linear terms, okay? Now, some of those aren't perfect. Some of them use things like i's and square roots and stuff, but we can definitely say that any polynomial breaks down into linear factors. So if you have a fifth degree polynomial, there are 5 linear factors that combine to make that polynomial. Okay, next up we have the rational zero test or the rational zero theorem. Okay, and what that tells us is if we're looking at a polynomial that leads off with an integer and ends with an integer. Okay, so key thing that the first number and last number are integers, we can create a list of the possible factors for that polynomial. And we'll use this list of factors or zeros to help us kind of break down this polynomial. Okay, now while this is great because it narrows down the list, it doesn't do a great job, and it still can lead us to some very, very complicated looking scenarios where we might have 14 or 15 different possibilities. And while we could sit around and test all of them, right, by using synthetic division, sometimes it's not necessarily the most practical thing. Okay, so let's take a look at real quick that rational zero theorem, and I'll show you a little bit of an example. So the rational zero theorem, I'm going to make up a polynomial real quick, and we're going to see how that might work. So let's say I've got 6x to the fourth minus 3x squared plus 17x minus, let's say, 2. Okay, now normally we would look at this polynomial and say, okay, can we factor it by grouping? Can we do something to help us break this down? And hopefully that would lead us to a 0. But if we couldn't do that, let's use the rational zero theorem to help us put together a list of possible rational zeros. Now, again, this is possible rational zeros. Not all of these are answers. They're just the possible answers that we could have. Okay, we could then trial and error and synthetic division our way until the end of the problem and figure out which ones are actually roots and use that to help us factor down this problem. Okay, and so what we do is we're going to take the last term, which is the number 2, and the first term, which is the number 6. So this number 2 is going to be my P, and that last number is going to be my Q. Okay, and so what happens is we take the factors of P divided by the factors of Q, right? So factors P over factors Q. And all of these are going to be plus or minus, okay? So here we go, let's make our list. And I tried to keep these numbers pretty simple because you'll quickly see how this can get out of hand, all right? So what are the factors of 2? Very simply, there's only 1 and 2, and we can go ahead and say, yeah, that's plus or minus, okay? And let's look at the factors of q, which is going to be my 6. So the factors of 6 are 1, 2, 3, and 6, right? 1 times 6 makes 6, 2 times 3 makes 6. And that's it. And these were pretty small numbers. And again, I'm going to go ahead and say, hey, these are plus or minus as well. Now, what does that actually mean? What does this list I've made mean? Okay, so here are some of the possibilities. It's any fraction that we can make from this list, right? So for example, maybe it's 1 over 1, right, from the first two, or 1 over 2, right? And of course, all of these end up being that same plus or minus. And then maybe we've got 1 over 3, and we've got 1 over 6. Not to mention we've got, if we move on to the 2 over 1, then 2 over 2, or just 1. And then we got 2 out of 3, and 2 out of 6. And some of these are actually repeats, you know, if I highlight them, maybe you'll see them. The 1 over 1 is actually the same as the 2 over 2, and the 1/2, or sorry, the 2 over 6 and the 1 over 3 are the same thing. Now, you can see that this list got really kind of messy without even having big numbers, right? Now, imagine if we had something like 12 and some larger number, right? Where there's a lot of factors. And suddenly you can end up with these huge lists of possible zeros, okay? So this is kind of a trial and error. It's a little bit brute force, and it's not necessarily the greatest. And that's why we made this note here that says, use this to factor when all else fails, right? So you couldn't find a better way to do this. Now we can rely on this list and then guessing and checking our way to the zeros, okay? So again, what did we do? We came up with a possible list of zeros. And those are from the numbers on top versus the numbers on bottom. We make any combination of those two, and it's always plus or minus. So actually, there were 16 possible numbers that we came up with based on that. And so you can see, hey, a lot of combinations, a lot of ways this could get crazy. So we try to find a good way to narrow it down instead. Okay, let's look at an example about putting together a polynomial. Here we've got a polynomial that has a root of 5, which has a multiplicity of 3, and some other zeros, 1/2, -3, and 9, all multiplicity 1. They tell us the scale factor is -2, and then they ask us, well, how many zeros does this have? Well, let's check it out. First, let's put this polynomial together. So I see the root of 5. So here we go, x equals 5 with a multiplicity of 3. And we've got x is 1/2, x is -3, and x is 9. And each of those just have a multiplicity of 1. So let's translate this real quick into a polynomial before we move any further. So here we go. We got x minus 5. That's cubed because of that multiplicity of 3. The next one, 2x minus 1. Okay, remember that 2 that was here came out in front here. We've got x plus 3 and x minus 9. And then they mention, oh, look, it has a scale factor of -2. So let's throw our -2 in front. And here we go. Here's my polynomial. How many zeros does this have? Well, let's just count them up. 1, 2, 3, 4. Okay. So we've got 4 unique zeros. Okay. Which means there are 4 solutions. Okay. And one of them is a repeat, right? That 5 is actually happening 3 times, but there are 4 zeros, okay, and the 5 repeats 3 times. Okay, so for this next problem, we've got a polynomial x to the fourth minus 6x squared minus 8x plus 24. And we're trying to find some of these zeros, the rational zeros for this. Okay, and kind of the first point is just where do I start from on this problem? And that's a really interesting point. Um, a lot of options. We could factor. Maybe if we could group or something, we might be able to factor. We could look at the graph, look for some zeros, or we could try that rational zero theorem where we write out the whole list and pick and choose zeros until we find something, right? So kind of one of the problems is maybe we should try factoring by grouping. So if you want to take a second, try factoring this. And you'll probably discover that grouping fails. So that's kind of bad news. We're like, darn, if we could have factored this, that would have made our lives way, way, way easier. But we kind of got stuck, and now we're going to have to find another way to break this down further. Let's try looking at the graph. So if we look at this graph, do we see any zeros or something that we might use as a starting point? So I'm hoping that you notice that on the graph, it looks like x equals 2 might have been a 0. So let's try that to start out. So we're going to start with x equals 2, and then we're going to use our synthetic division to help us break this polynomial down. Okay, so let's set up synthetic division with 2 and this polynomial. So here we go. You can see I set up the polynomial division line, and I made sure to fill in my little 0 right there. Okay, let's go ahead and drop our 1 down, multiply, add these together, multiply, add them together, multiply, add these together, and let's multiply again, add them together, and hey, look, good news, we got that 0 as our remainder. That's some good news that we got this to factor properly. Okay, so now that we got that 0, let's write out the factored form just so we can kind of see where we're at right now. So we've got this 2 leaves me with x minus 2 as a factor. And this, remember, is 1 power less than what we started with. So x cubed plus 2x squared minus 2x minus 12. Okay, and so here's where we're at. We've broken this down at least, and we know that one of my zeros is, and so I've just noted that off to the side, hey, x equals 2 is one of my zeros. And let's continue on this path of solving for more zeros. Now, I noticed when I was looking at my graph, this graph bounces at that 2. So maybe it's a double root. Let's try that same 2 again. And again, I'm going to factor this portion now. Okay, so we're going to do the same thing. We're going to use division again. And let's set it up and divide. So we're going to put that 2 back on the bar. And we've got 1, 2, negative 2, negative 12. And we're going to follow the same process, right? Bring it down, multiply, add, and then multiply, add. And again, we got that 0 as our remainder. Good news. So again, this 2 seems to be a repeat. Okay, so this is a repeated 2. And where do I stand now? I've got x squared plus 4x plus 6. And we've got, don't forget about our x minus 2. And, oh yeah, this one that I just divided out is another x minus 2. And you might just write x minus 2 squared. But there we go. And maybe we could look and say, hey, can this factor down any further? Well, this piece does not, right? So this piece I underlined in green does not factor. So if we wanted to solve this further, we would definitely need quadratic formula or maybe some other method to solve it. But for now, we're just going to stop because these are our rational zeros right here. Okay, So the only rational zero is 2 with a multiplicity of 2. And as for the part that didn't factor, maybe I wanted the complex or the irrational zeros, so we could go ahead and use the quadratic formula to help us solve this. Now, on the previous question, if we had continued down the road of using the quadratic formula, we would have gotten another pair of answers. And I would have told you that those answers were actually a conjugate pair. Okay. So a conjugate pair is the pair of numbers that are either irrational or, in this case, complex, right? And remember, it's a plus bi and a minus bi. Always that imaginary portion has a flipped sign. And those zeros, the secret is they just always go in pairs. They're always a couple, right? The moment that you've got one of them, you must also have the other one, right? So here's an example. I've got a fourth degree polynomial that has these roots, -1 twice and 3i. Well, wait a minute. Many of you math wizards will have noted, wait a minute, -1, that's 1, plus 1, and here's another x plus 1. Well, how do I get 4? I've got x minus 3i. Well, here's the thing. The moment I saw this 3i, I knew that its partner was also coming along. So negative 3i is also a 0, okay? It has to be. The moment you have one imaginary number, you always have its conjugate, okay? So we've also got x plus 3i in this case from that conjugate. Now let me note, we hate leaving things in this form. This form is terrible, all right? So we're going to go ahead and combine this portion together. Now, you may realize that we could FOIL this out the long way, or we might notice that, hey, minus and plus, so something's probably going to cancel out. So if I just FOIL this out one time, x squared plus 3xi minus 3xi minus 9i squared. And this is going to simplify down pretty nicely for us, actually. These go away. 9i squared just flips the sign. X squared plus 9. Ooh, looked like it was going to get ugly for a second. And hey, look at these x plus 1s. I'm just going to rewrite them as x plus 1 squared. And boom, here is my polynomial. Okay? And that has a degree of 4 and has real coefficients, okay? So make sure that you multiply it out, otherwise you don't have real coefficients, okay? Don't leave your equations with I in them. Earlier in the video, we talked about factorizing polynomials, and we mentioned that you can break any polynomial down into linear factors, okay? And some of those will have some complex numbers as pieces, but they will always be able to break down into linear factors. And in this note, we've kind of mentioned, like, hey, once you factor it down, you might get stuck, but you can still actually continue to break a polynomial down further by using the quadratic formula to find the complex and kind of those funky looking roots. Let's look at this example. They gave us this polynomial x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. And they said 1 plus 3i is a 0. Okay, I'm hoping some alarm bells are going off in your head based on what I just told you earlier. That, hey, if 1 plus 3i is a 0, there's got to be another 0 that goes with it. What is that 0 going to be? I'm hoping you came up with 1 minus 3i because that's the conjugate pair for it, okay? So remember, complex zeros always come in pairs, okay? So 1 plus 3i means 1 minus 3i is also coming to that party, okay? And let's see what we can come up with. Before we even look at our function, let's see what these two factors have told us. If I write them out as factors, here we go, x minus 1 plus 3i and x minus 1 minus 3i. So there we go. At least I've written it out as actual zeros. And again, man, i's kind of aren't the greatest thing for trying to divide and factor and stuff. So let's see if we can put this all together and maybe we'll get something that looks a little bit nicer. Okay. And I'm going to start by actually distributing this negative sign. And I've got x minus 1 minus 3i and x minus 1 plus 3i. And we can go ahead and distribute this out. So x squared minus x plus 3xi. And I'm just lining my terms up as I go. So we got minus x plus 1 and then minus 3i. Okay, so that was distributing to 1 and then minus 3i. So we got minus 3xi plus 3i and minus 9i squared. Okay, so canceling some stuff out here, and this looks kind of ugly to start out, but actually a lot of this stuff cancels out. Minus 3xi and plus 3xi, we got minus 3i and plus 3i canceling out, and we can actually simplify this last piece down pretty nicely as well. I squared is going to become positive 9 instead of minus 9. So here we go, we got x squared minus, there's two x's, and 1 and 9 make a 10. So there we go. We got x squared minus 2x plus 10. And this piece right here is a factor of the polynomial. Okay. So what does that mean for us? That means we can use this to further break down the... So in this case, since everything is quadratic and to the fourth power, we're going to need to use long division. So this could get a little bit crazy looking, but let's set it up. X squared minus 2x plus 10, and inside of here is going to be x to the fourth minus 3x cubed plus 6x squared plus 2x and minus 60. Okay, so now we're going to have to use long division, and this gets kind of tedious. But if we follow through and do all of our division, right, we're going to get a x squared, and we got x to the fourth minus 2x cubed plus 10x squared. Subtract the whole thing, okay? Always canceling that. Minus x cubed minus 4x squared plus 2x, bringing down that one. And we're going to repeat this process again. Same thing again. X squared to this minus x cubed plus 2x and minus 10x. Subtract, and we've got 6x squared, and this is going to be plus 12x, and of course bring down that 60 at the end. And finally, last time we're going to multiply by minus 6, and we should see that this is going to perfectly cancel out. And now that we've canceled this all out and we get that remainder of 0, we know that these are the two factors of the polynomial we started with, right here and right here. So let's see what our factored out polynomial is right now. We've got x squared minus 2x plus 10 and x squared minus x minus 6. And maybe we can figure out what the zeros are from there, because remember we were saying let's find the rest of the zeros. So the first thing, we've already got two zeros from this piece. We already knew those. There's x equals 1 plus 3i and x equals 1 minus 3i. Okay. Let's find a couple more from the other piece. Well, lucky for us, this piece factors. We've got x minus 3 and x plus 2, which is going to give us some simple zeros, x equals 3 and x equals negative 2. So here we go. Here are some real zeros, and here are some complex zeros from that problem. Okay, so this problem is kind of lengthy. Why? Because we had to take the time to put together one of the factors and then divide. Okay, now the rational root theorem doesn't always eliminate a ton of zeros, and not everything factors super nicely with it. So we have another piece of information that may be helpful to us, and this is Descartes' rule of signs. Okay, so Descartes came up with this rule that helps us determine what kind of zeros there are more of, positives, negatives, or imaginary. Okay, and what we use in this is looking at sign changes. Okay, and they refer to this in your book as variation in signs. Okay, and basically you're just looking for, once you put everything in standard term, how many times does the sign flip as you go from term to term? Okay, so let's go through it together and see what information we learn. Okay, so we can start by rewriting our polynomial. 3x cubed minus 5x squared plus 6x minus 4. And let's mark wherever we see signs changing. So going from 3x cubed to negative 5x squared, that's a sign change. And going from negative to positive, so that's 1, 2, and 3. And that means there is a maximum of 3 positive zeros. Okay. And basically, when you count these, you always count up and down by twos because of the imaginary zeros. They always come in pairs. Okay. So I'm just going to go ahead and put this, it's 3 or 1 right now. All right. And I will explain a little more about that in a second. Let's go ahead and try to do the negative zeros. Okay. So when we want to do Descartes' rule of signs for negative zeros, we have to do f of negative x, which means basically just replace all your x's with negatives. Remember to always put parentheses when you do this. Okay. It can seem tedious, but it will save you from screwing something up. And remember, every point matters in this class. So here we go. And this one's going to stay negative. And this one's sign actually cancels out. So it just stays the same. Minus 6x minus 4. And you'll notice, guys, odd powers keep signs, right? Even powers, they go away. So it only changes the odd exponent terms. And what you'll notice is there are all negative terms, right? So there are no sign changes here. Okay, which means how many negative zeros do I have? None, absolutely, right? So if I started to try and use the rational root theorem on this, right, I would have had maybe like 16 different zeros, plus or minus, okay? Well, if we relied on the rule of signs, in combination with that, we can eliminate all of the negative answers, right? You already told me there are no negative answers. So all we could do is come up with, hey, there have to be only positive answers for this one, okay? And I know for a fact there's at least one, right? Let's see how we can keep track of this information. We use a little chart called a P and I chart, right? So P and I stands for positive, negative, and imaginary. And what you got to remember is the number of total zeros can't change. It's always got to be equal to the degree. Okay, so my total is always going to be 3 because of the degree. So let's put it this way. Let's see how many ways we could put this together. Well, if I've got 3 positive zeros, I've got no negative zeros, and I have no imaginary zeros. But let's shift some of that balance around now, right? The total's still 3. Well, maybe I only have 1 positive zero, 0 negatives, and those 2 that I was missing are now in the imaginary column, okay? And remember when I mentioned before, hey, we always have to count down by 2s? Well, guess what? Remember that imaginary numbers always went in pairs. Those irrational and imaginary and complex roots always had their conjugate with them. Well, here you go. This is why we always have to count by 2s. Okay. Now, if I had had some negative zeros that were possible, we would have also had those in there, and we could fiddle with the list in a lot of different ways to come up with some combinations. Okay, but this P&I chart helps you kind of track how many zeros are available and in what combinations we could put them together, right? So in this case, I know that at least at minimum, I've got one positive answer, and maybe I've got up to three positive answers as zeros here. Okay. Take a minute, go back, think about the rule of signs, and make sure that you understand how you could put the zeros together. Okay. And go back through that process and summarize it at the bottom of this page. Okay. All right. Happy studying. Hope this video was helpful, and good luck.